Good evening, everybody. Buenas noches. Welcome to day 2 on week 9 of the semester. On Tuesday, the last thing that we were talking about was naming alcohols. So we were understanding alcohols in terms of it. This is one of the functional groups that is present in carbohydrates, okay? And even though the topic of naming alcohols may not be in the textbook, I think it's very important, specifically in Chemistry 112, that we understand how to name certain functional groups, including alcohols. So as you can see here, we did the example on the top with a condensed structure, and you guys helped me just figure out what is the longest carbon chain, what are the substituents, and how do we name it. We have 2 more problems down here. So let's focus specifically on this molecule right here, which is a skeletal structure that we have in alcohol, and we also have a halogen, okay? So at first, let's utilize the chat. How many carbons do we have in the longest carbon chain for this molecule? Great job, you guys. Excellent. 4 carbon atoms, okay? Remember that according to the rules, we're going to start numbering the carbons, starting from the end that is nearest to the carbon that is holding the OH. So when it comes to this is going to be carbon 1, this is 2, this is 3, this is 4, okay? So what will be the name for an alcohol that has 4 carbons? Remember, we have the alkane name, we take away the E, and we put OL ending to it. Excellent, great job, Isaiah, Kiyomi, Kate. Oh, people are just rocking this. Excellent job, you guys. Butanol. So, butanol is going to be the name of our alcohol. And you can see that we have to give the position of the carbon that is holding the OH, which is carbon 2. We have 1 substituent on 4, okay? If we have a bromine, what is the name that we utilize to symbolize that bromine? So what is the name when bromine is a substituent? Excellent job. Great to see that on the chat. So this is a bromo group. So the name of this molecule is 4-bromo-2-butanol, okay? So I have one more example here for you guys, which is, alcohols can actually be cyclic, okay? And in chapter 4, we learned how to name cyclic alkanes. So this is not going to be as different in terms of like, oh, okay, so if I look at the cyclic system, what would be the name of it? Now we are applying all that knowledge to naming cyclic alcohols, okay? So this structure that we have in cyclic form, what would be the name if it's an alcohol? Again, we're going to apply the same rules that we did for the alkanes that we just named here. We write the, in this case, cycloalkane name in N-N-O-L. You guys are just processing this beautifully. Excellent job in the chat. Cyclopentanol is the correct name for the cyclic alcohol. So remember that that is going to be the name of our parent chain. Now, when we have a cyclic alcohol, understand that the carbon that is holding the OH is going to be carbon number 1. This is specifically for cyclic alcohols, but similar to how we were naming cyclic alkanes before, then we have to, number the rest of the cyclic system clockwise or counterclockwise to give the rest of the substituents that we have here. And in this one, we only have 1, the lowest number, right? So what do you guys think? Let's put a 1 in the chat for clockwise, a 2 in the chat for counterclockwise. Oh, people are already answering. You guys are in a roll. Exactly. We have to number this counterclockwise. 2, 3, 4, 5. So at position 2, what substituent do we have? Let's put that in the chat. What substituent do we have on 2? Isaiah got it. Not iso. You actually had it the first time, Isaiah. Remember that when it comes to the propyl flavors, we have 2 of them, right? If I write in the carbons and hydrogens, this is a CH2, this is a CH2, this is a CH3. So my substituent is attached to the main chain, which is the cyclic portion of this alcohol via the CH2. So understand that that means that this is a propyl group. Isopropyl will be if we will be attached through this carbon, the middle in the propyl. Put a 1 in the chat if that makes sense. Great to see those 1s. Awesome. So the name of this molecule is going to be 2-propyl cyclopentanol. It's all one word, okay? It's just that, you know, because I wrote it in pieces, you see a space, but understand that this is all one word. Questions on naming alcohols? Should we do at least one more practice problem? Go ahead.
I was just saying, for the OH, since it's coming off the, like the 1, wouldn't it be 2-propyl 1-cyclopentanol, or do we not need to write it? If
that is an excellent question. So when we have cyclic alcohols, you don't need the 1-cyclopentanol because it is assumed that the OH is sitting on carbon 1. What is important is to put the number for the substituent, because as you can see here, the OH is pointing kind of to the side, and we know, and it is assumed that the carbon that is holding the OH is carbon number 1. So it's kind of redundant to put the 1-cyclopentanol, because in essence, every single, at least for the molecules that we see here, every single cyclopentanol will have a 1 at the cyclopentanol level.
Gotcha. Thank you.
No problem. Put a 2 in the chat if you want to do at least one more problem, you know, a brand new structure, and we get to name it. Awesome. So this is from a different worksheet, but I just want you guys to at least be able to name molecules. So this is not actually from our in-class worksheet, but just understand that I want to be able to give you guys problems. Because when I post chapter 6 homework, you will be naming some of these. So let's at least practice. So I'm going to give you guys a couple of minutes, find the longest carbon chain, okay? And then write the name of the parent chain. And in this case, we only have 1 substituent. Remember that the rules that we learned in chapter 4 for naming organic compounds will be utilized throughout, okay? So let me give you guys a couple of minutes. At 6:21, we will be going over the answer, unless people are ready. When you are ready with your answer, put a 3 in the chat so I see how many people are done. Ooh, Isaiah is ready. I already have 1. Kiyomi's ready. 2 students. I have 11 students here. Let me see. There's 2 ready. There's 3 ready. 4 ready. Let me get at least 7 of you guys ready. Ooh, we're getting there. 1 more. I need to see 1 more 3 in the chat. Let me see, one more 3. Let me see who else is done naming. We have about 1 more minute. I need 1 more 3 in the chat and we will go over the answer. There you go. We got that 1 more 3. If you didn't, get to do it, it's okay. Just follow the steps that we're about to do, okay? So at this time, let's put in the chat, how many carbons do we have in the longest carbon chain? Love to see those 7s. Excellent job, you guys. 1, 2, 3, 4, 5, 6, 7. For this molecule, I numbered from right to left because remember that CH3 at the end is going to be the end that is nearest the carbon that is holding the OH, okay? So now let's put in the chat, if you have 7 carbons in a row and we have an alcohol, what will be the name of that parent chain? Great job, I agree. You guys got this. Heptanol. And like Maria put, this is 2-heptanol because carbon number 2 is holding the OH. How many substituents do we have? Let's put it in the chat. How many substituents do we have? We have 1. So let's put location and name for it. Great job. So on carbon 4, we have a bromo group. Remember, whenever we have words and numbers, we always separate them with a hyphen or a dash. Okay. Just 1 more. Let's do this one. I'll give you guys a couple of minutes. When you're ready with the name, just put it in the chat. We will go over it in detail, but I just want you guys, look at it, follow the rules, put it in the chat. Maria, that was a great first attempt. What you're missing is the cyclo. Where would the cyclo be? But that was a great first attempt. Great job, Isaiah. Yes. Great job, Maria. That's a great way to correct it. Okay? As you guys are working through it, I'm just going to go through the process on how to name this one. We have a hexagon, okay? And this hexagon has a hydroxyl group. So like some students put on the chat, this is cyclohexanol. Okay? The carbon that is holding the OH is going to be carbon 1. Okay? Put a 1 in the chat if so far makes sense. Excellent. Good to see those 1s. Now, in this molecule specifically, we have 2 substituents aside from the OH. And because of their position, it doesn't matter if we go clockwise or counterclockwise, they're going to be in the same numbering, okay? So let's say that I go clockwise. This is carbon 1, this is 2, 3, 4, 5, and 6. As we learned before, when we have multiple of the same substituent, this is going to be a substituent that is called chloro. In this chloro group, because we have 2 of them, we're going to put dichloro to symbolize that we have 2 of them. And lastly, we're going to give their positions separated by a comma. So at position 3 and at position 5, we have 2 chlorines, okay? Put a 2 in the chat if it makes sense. Great. So let's go back. To talk about the other 2 functional groups that are parts of carbohydrate structures. And you guys can see that the first one that I'm illustrating on how to name is an aldehyde, okay? So remember, aldehydes are going to have that carbonyl that is bonded to one side to a hydrogen atom. So when we are naming aldehydes, understand that you're going to find the longest carbon chain that it has the CHO group. For those of you that may be like, wait, what is the CHO group? This CHO group is just representing this, okay? Or in the case of the bottom molecule, it's going to be that, okay? Now, understand that the longest carbon chain must contain the carbonyl with the hydrogen. So that carbon in the double bond with oxygen and in the single bond with hydrogen needs to be contained in the longest carbon chain. You're going to write the alkane. In this case, because we have an aldehyde, we're going to replace the E ending with AL. So all our aldehyde names are going to end with AL, okay? And as you can see, you're going to number the chain. Specifically for aldehydes, carbon number 1 is always the CHO group. So the carbon in the carbonyl that is also bonded to the single bond hydrogen, that's carbon number 1. And then after that, we're going to give the locations and the name of the substituents as a prefix according to the rules that we already learned in chapter 4. So taking that into consideration, here I have the following aldehyde in condensed form. Take a moment, count the number of carbons in the longest carbon chain for this aldehyde. And let's put it in the chat. What is the number of carbons in the longest carbon chain in this aldehyde? Excellent job, you guys. I agree with you. There's 6 carbons. So remember, in an aldehyde, carbon number 1 is the one that is the CHO group. So the carbon in the CHO group, that's carbon number 1. And then we go 2, 3, 4, 5, 6. Let me just erase, or at least let me just keep this to be consistent with the labeling, but let me just highlight the longest carbon chain here. Now, we have 2 substituents here that are the same. And that's going to be the prefix to our parent chain. But let's put in the chat, what will be the name of the parent chain here? So we have 6 carbons and we have an aldehyde. Remember the rules, alkane name, take the E and put AL. Excellent job, you guys, in the chat. Hexanide. Now, because aldehydes, we know that carbon number 1 is always going to be the carbon in the CHO group. We don't need to put 1 hexanyl. or any aldehyde. You don't have to put one and then the parent chain, okay? What we really need to put is the substituents that are here. So based on you guys' knowledge on how to put substituents, put in the chat, what will be the way that we name these substituents? Great job in the chat, you guys. 3,4 dimethyl hexanal. Okay. Now, some aldehydes actually have a special name. And I wanted to introduce you guys to one of those aldehydes that actually have a special name. So, when you have a CHO group, okay? And for those of you that need to see the carbons, there's a carbon right here. So that's why that is a CHO group, right? When that CHO group is directly attached to a benzene, that whole thing, which I'm going to highlight right now, let me just change the thickness of this. When we highlight, you know, this whole thing, okay, this is going to be like a signature molecule, okay? A benzene ring attached to a CHO group. So that whole thing has a very specific name. And that specific name is benzaldehyde. Okay. Now, how do we deal with benzaldehydes? Well, the carbon that is holding the CHO in the benzene ring is going to be carbon number 1. And then, similar to how we have numbered other cyclic systems, we have to decide if we go clockwise or counterclockwise. So utilizing 1 for clockwise, 2 for counterclockwise, which one should we number this cyclic system to give the other substituent here? Great job. I agree 100%. We should go counterclockwise. So this is carbon 2, this is carbon 3, 4, 5, 6. So we know that in carbon 3, we have a substituent. What will be the name of that substituent? What are those lines representing, you guys? Let's put it in the chat. Excellent. I love those answers. Correct. That's an ethyl group. So to name this molecule, this is 3-ethyl benzaldehyde. Okay. Put a 1 in the chat if you want to practice at least, you know, 2 problems naming aldehydes. Great. We're going to practice these 2 molecules. We're going to name them. So I'm going to give you guys a minute each. Let's name these 2 aldehydes, and then we will go over the answers. Great job. I already named the first one. That is awesome. And that's a really good name. Keep up the good work. Continue to the other one. And for the students that are still working on it, put in the chat if you agree with Isaiah's name for the first molecule, the one on the left. Awesome. Great job showing support to your colleagues here. I agree. For those students that need to see the work done on the molecule, this is carbon 1, this is carbon 2, this is carbon 3, 4. So on carbon 2, we have a methyl group. And then there's a butanol now. Great job. Let's continue to the next one. Great. So Isaiah and Kiyomi put it in the chat. So out of those two, we just have a few spelling issues with Isaiah's, but hey, that's okay. You did your best. Kiyomi, that is the correct answer, okay? So this whole thing is your benzaldehyde. Cheer for Kiyomi too in the chat, people. So this is carbon 1. And in this case, it doesn't matter if we go clockwise or counterclockwise. Come on, nobody's showing love to Kiyomi? Thank you, Isaiah. He's showing support. Thank you, Kiyomi, for the answer. So this is 2, 3, 4, 5, 6. Hey, we just need to be supported. Thank you guys for cheering Kiyomi on. This is what we're family here. And then the name of this molecule will be 4-methyl benzaldehyde. Questions on naming aldehydes? I agree, Katie, 100%. Great theme, Dominique. I love that. One team, one dream. To get A's in Chemistry 112, that's the dream. And I know you guys can achieve it. You guys are rocking this class. Any questions? Naming aldehydes. Put a 1 in the chat if you're ready to learn how to name ketones now. Great. Let's go back. Now we're dealing with the ketones. So, as you can see, ketones, and I'm just recalling some of the information that we learned in chapter 4. Ketones are going to have a carbonyl, and remember that the carbonyl is a C double bond O that on either side is going to have carbon chains, okay? That's what makes it a ketone. As you can see here, on the top, we have the condensed structure for a straight chain ketone. On the bottom, we have a structure for a cyclic ketones. So ketones can be cyclic, okay? Now, you can see that when it comes to the rules, you're going to name the longest carbon chain by replacing the E in the alkane name by the ending -one. This is one of the things that I really like about naming in organic chemistry. It's kind of like the functional group tells you what's the ending. Or when you see a name, you can be like, oh, it ends in -one, that it has to be a ketone, or it ends in Al, that must be an aldehyde, or if it ends in OL, that's an alcohol. So as you can see, the name kind of tells you the identity of the molecule that we're discovering. So continuing on step 2, we're going to number the carbon chain starting from the end that is near the carbonyl group, okay? And then we're going to give the location and the name of the substituents at the prefix of the name. Understand that for the ketone, similar to how we treated alcohols, we need to give the location of the carbon that is holding, in this case, the double bond oxygen, okay? So let's get started with the condensed structure. How many carbons in the longest carbon chain? Great job. 5, okay? Let me number them. Let me actually highlight them first. Those 5. Okay, we're going to start numbering from the end that is nearest the C double bond O. So when it comes to numbering this, we're going to say 1, 2, 3, 4, 5. Okay. So as I mentioned, we put the alkane name, we take out the E and we paste an O-N-E. So we put an own. So if we have a 5-carbon ketone, what would be the name? Great attempt, Katie. We're missing a letter. Let's just fix it really quick. Remember that? Great job fixing it. And the other students that are putting the word on the chat. Exactly. So the name of the parent chain here is going to be 2-pentanone. And we only have one substituent. Oh, see, that's why I love this crew. Thank you for supporting each other on the chat. That's important. Number and name for the substituent in this ketone. Great job, you guys. 4-methyl, 2-pentanone. Okay. Let's deal with the cyclic ketone. So similar to what we've done before, in this cyclic ketone, understand that the carbon chain is within the ring, okay? So based on the shape that this has, what would you guys suspect is the name of this cyclic ketone? Let's put it in the chat. Great job, Dominique. Exactly. This is cyclohexanone. So what would you guys suspect that is carbon number 1 in the cyclic system? What would be carbon number 1? I agree. Thank you, Vanessa. The carbon that it has the double bond to the oxygen. That's carbon number 1. Now, similar to what we've done throughout, and it happens to be that many of the ones that I showed have the same thing. So don't assume that that's always the answer because we know better. But in this case, do we go clockwise or counterclockwise? Clockwise is 1, counterclockwise is 2. Yeah, counterclockwise. I know that most of the examples that I've given you guys is counterclockwise, but please don't assume that it's always counterclockwise. It depends on where the substituents are. It just happens to be this way. So we have 2, 3, 4, 5, 6. So similar to the cyclic alcohols, cyclic ketones, because as long as the carbon double bond to oxygen is attached to the ketone and attached to the cyclic system, I am not giving you guys other types of ketones where the ketone motif is outside of the ring. We're not dealing with those in this class. So because carbon number 1 is always the C that is holding the double bond to oxygen, we don't need to put 1 cyclohexanone. Give me one moment. So in this case, we have 2 substituents, 1 on 2 and 1 on 4. That is a great attempt, Katie. But the thing is that we need to put it, thank you, Isaiah. We need to put them in alphabetical order. Don't forget that. Alphabetical order. Like you can put the numbers, but then when we align them, it has to be in alphabetical order. So thank you, Isaiah. So when it comes to this, it's going to be 4 ethyl, 2 methyl, cyclohexanone. Put a 1 in the chat if you want to try at least 2 problems. Great. Let's see, do I have another cyclic? Let's do this molecule and this molecule. The ones that I highlighted in green. So I'll give you guys a couple of minutes. And if you're ready, put the name for the molecule in the chat. The number of carbons in the parent chain is not correct, Isaiah. That's the only thing you need to correct. Great job, Katie. I agree with you. 1, 2, 3, 4, 5. But the beginning was okay, Isaiah. So be careful with counting the number of carbons. Come on, people. Let's clap for Katie. She got it. Thank you, Isaiah. 4, 4, methyl, pentanol. Let's do the cyclic ketone. It is a triangle. Whenever you're ready, put it in the chat. Great job, Dominique. Vanessa, we just have to fix the back, the parent chain. Great job, Maria. So, carbon 2. Oh, let me just number the carbon atoms. This is 1, this is 2, this is 3. On carbon 2, we have an isopropyl group. And then this is cyclopropanol. Okay. Put a 1 in the chat if alcohols, aldehydes, and ketones make sense. How to name them. Awesome. So let's go back to talk about carbohydrates. Okay. Now, when it comes to carbohydrates, we can actually classify them based on the carbonyl that they have and the number of carbons that they have. Okay. So as you can see, monosaccharides can have 3 to 8 carbons in chain in the longest chain, and is going to have a carbonyl functionality. If your monosaccharide has an aldehyde, that is known as an aldose monosaccharide or as an aldose sugar. If your monosaccharide has a ketone group, that is known as a ketose. Okay. So again, the hydroxyl groups here are going to be present, but we're going to focus on 2 things: number of carbons, and then does it have an aldehyde or does it have a ketone? When it comes to the number of carbons, we also have words to identify the number of carbons in my monosaccharide. As I mentioned a few moments ago, monosaccharides are going to have anywhere from 3 to 8 carbons in length. So for example, if your monosaccharide has 3 carbons, that is known as the triose. If it has 4 carbon atoms, that's known as the tetrose. If it has 5 carbon atoms, that is a pentose. If it has 6 carbon atoms, that is a hexose. Now, remember, from 5 carbon atoms on, we always use prefixes. So what would you guys suspect is a 7 carbon atom monosaccharide? What would be the name? We use the prefix and we end it with O's. Great job in the chat. Hexose. What about 8 carbon atoms in a monosaccharide? Excellent, you guys got this. And octose. Now, those 2 classifications, we can do them individually or we can put them as one word. And as you can see here, we have 2 different monosaccharides. We have glucose and we have fructose. If we number the carbon atoms on each of them, we can see that they have 1, 2, 3, 4, 5, 6 in the case of glucose. And in the case of fructose, we have 1, 2, 3, 4, 5, and 6. So that's why both of them are known as hexose sugars. Okay? Put a 1 in the chat if the word hexose makes sense based on the number of carbons that we have. Great. Now you see that before the hexose, we have a particular prefix. We have aldo in the case of glucose, and the aldo comes from having an aldehyde. In the case of fructose, see how it says keto? Okay. And it's because there's a ketone in the structure. Okay. So for ketose monosaccharides or monosaccharides, if we have to put the combo classification, meaning functionality in terms of the carbonyl and number of carbons, we don't write ketose hexose, we just put keto. We don't write aldose hexose, we just put aldo. Okay, so let's actually visualize this concept by practicing here. Okay, so I want you guys to take a moment, and out of these 4, let's classify these 2. So the first molecule on each of the 2 rows. So take a moment, classify it, as you can see in the instruction, according to their number of carbons and carbonyl functionality. Let's classify those monosaccharides. Okay. The first molecule on the first row, so this one, does it get an aldo or does it get a keto? So A or K, let's put it in the chat. Aldo or keto? Great, you guys got this. Aldo. How many carbons? So what word am I going to put after aldo? Be careful. We don't use bute, tetrose, but that's a good one. I always say that, like, and I sometimes put it in exams too, to see who is paying attention, or who'll be like, yes, bute because of organic, but no, there's not butose. I put an exam. I just need to see who is, really paying attention versus who is just, oh my God, I don't know. I'm just going to just follow through. So, But great job, Dominique. Okay. Let's look at the second molecule that we have. Is that an aldo or a keto? Great. Which, by the way, the keto in the keto diet is because of ketones. Just putting it out there. I don't know who knew that. Put a 1 in the chat if you knew that. Oh, there you go. Some of you guys knew that. Awesome. Let's see. For those of you that didn't know, yeah, it's all relevant. It's all organic chemistry. Counting the number of carbons. Great job, Maria. Yes, this is a heptose. So this is a ketoheptose. Questions, classifying monosaccharides. Pretty straightforward, right? And you can see I gave you different flavors, and in the in-class worksheet, there's different monosaccharides there that you guys can classify, okay? Now, another classification that I mentioned verbally in the last chapter, in chapter 5, but I want to make sure that you guys, solidify that concept, will be the classification of alcohols, okay? Because it is also incorporated in chapter 5 homework, okay? So alcohols can be classified depending on the carbon chains that are bonded to the carbon that is holding the OH, okay? So as we can see here, if the carbon that is holding the OH has one carbon chain, it doesn't need to be a CH3, one carbon chain, that is known as primary. And the symbol for primary is like that degree sign, but we just call it primary. If the carbon that is holding the OH is attached to two carbon chains, then that is known as secondary. And as you can see, if the carbon that is holding the OH has 3 carbon chains attached to it, that is 3 carbon chains. That is known as a tertiary alcohol. Okay? And remember that in the previous chapter, we saw how primary alcohols can turn into aldehydes. Aldehydes can turn into carboxylic acids. Secondary alcohols can actually make it, be converted to ketones, and ketones can be reduced back to secondary alcohol. So just keep this in mind. To practice, I just want to do at least these 2 molecules, okay? So that cyclic alcohol that we have on the left, let's put a number, 1, 2, or 3. Is it a primary? Is it a secondary? Or is it a tertiary alcohol? It's not primary. Let me just write in the carbons, maybe illustrate it. This is a carbon that is bonded to a hydrogen, and that's the one that is holding the OH. That is bonded to this carbon, and that is bonded to this carbon. Excellent. Thank you, Maria. That is a secondary. Put a 2 in the chat now if it makes sense. Why is it secondary? Because the carbon that is holding the OH is bonded to 2 carbon chains. Let's look at the alcohol on the right. Is it primary, secondary, or tertiary? Let me write in the carbons and hydrogens. This is the carbon that is holding the OH. It's a carbon with a hydrogen. This is a CH3. This is a CH. This is a CH2. This is a CH3. So what is the classification of that? I agree. This is a secondary. This is a primary. Okay. Put a 4 in the chat if classifications of alcohols makes a little bit more sense. Great. Now that we know what is a monosaccharide, what are the functional groups in there, we know how to name those functional groups outside of the monosaccharides. Let's now see how monosaccharides, even though I've been showing you the structures, how they're actually illustrated in their more common conformation. Most of the time, whenever we are illustrating monosaccharides, we utilize Fischer projections, okay, to illustrate monosaccharides. And a Fischer projection was actually invented by Emil Fischer, okay? And as you can see, this was invented in 1891. And this is a 2-dimensional representation of a 3-dimensional organic molecule. Because when it comes to the carbon atoms that you have in a Fisher projection, understand that those carbons are going to be tetrahedral, at least the ones in the body of your monosaccharide. And you can see here that the ones that are tetrahedral are going to be carbon 2, 3, 4, 5, and 6. The only one that is trigonoplanar is carbon 1, okay? Now, taking this into consideration, because carbons 2 through 6 for glucose are tetrahedral, understand that in that tetrahedral conformation, those angles are going to be 109.5, and we basically are going to be illustrating the carbon atoms by location in terms of the intercept that we see in the Fisher projection. So even though you don't visually see carbons 2 through 5, we know that they are sitting right here. The reason why this is illustrating a 3D structure is because when you look at the electron group geometry of those carbons, then those angles, instead of being illustrated with wedges and dashes, we're just going to use lines, okay? And that's the logistics of a Fisher projection. So understand that this is one of the most common ways that we illustrate monosaccharides. Now, stereochemistry is coming back because we need to understand that when it comes to carbohydrates, and in particular monosaccharides, they are going to have different conformations, okay? When it comes to the stereochemistry of monosaccharides, let's establish that when it comes to monosaccharides, we're going to have two different conformations, okay? One is the L conformation. The other one is the D conformation, okay? And how do I identify it? My monosaccharide is L or D. Well, as you can see here, the D or L isomers are assigned according to the position of the OH on the chiral carbon that is the farthest away from the carbonyl. So when we look at the molecules that we have here, erythros in the L conformation and erythros in the D conformation, okay? Let me just look at these closely. We can see that the carbonyl is right here, right? And this is an aldose sugar. Now, this aldose sugar has 1, 2, 3, 4 carbon atoms, okay? There are 2 chiral centers on erythros. Put in the chat, what are the 2 carbons that are chiral in erythros? What are their numbers based on the numbering that I gave you guys? Great job, Dominique and Maria. Exactly, carbons 2 and 3. For those of you that are like, wait, what? Chirality, what? I erased that once I finish exam 2. Don't erase it, it's going to keep on coming back. So the reason why carbon 2 is chiral, let me just review. As you can see, it's bonded to the aldehyde motif. It is bonded to a hydrogen. It is bonded to an OH. Carbon number 2 is bonded to all of it. Those are the 4 things that is attached to, okay? Carbon number 3, let me just erase some of the things that I highlighted. Carbon number 3 has the OH that you can see there in green. It has the H. It has this, and it has a different color. And it has all of it. So those are the 4 groups around carbon 3. Carbon 4 is not chiral because it has 2 hydrogens. And carbon 1 is not chiral because it only has 3 groups. In order for you to be a chiral carbon, you need to be tetrahedral. Okay? Put a 1 in the chat if it makes sense why 2 and 3 are the only chiral carbons in erythros. Great. Now, 3 is the chiral carbon that is the farthest away, okay, from the carbonyl functionality, right? Is the one that is more away from it. And as you can see here, all you have to do, you guys, is look at where the OH is. If the OH is on the left side, then that is the L isomer. If the OH is on the right, okay, on the, if you know Spanish, it's on the derecha side of your monosaccharide, then that is the D isomer, okay? So you may be wondering, Dr. Luz, why do you have a picture of Samuel L. Jackson here? This was just a meme that was sent to me when I was in grad school. And I was like, this is just the perfect way to explain L and D, okay? So we know Samuel L. Jackson, and you can see Samuel L. Jackson, he's looking to the left, okay? Samuel D. Jackson, as you can see, is looking towards the right, meaning looking towards the derecha, that means that that is the D isomer. Maybe it works for you, maybe it doesn't work for you, but it's a good reminder of L and D isomers. One more thing that I want to mention when it comes to D and L isomers, when it comes to stereochemistry, the relationship between these two is that they are enantiomers. You can see that the L is, or the D isomer and vice versa, is the mirror image of the L isomer. The groups are reflected, okay? So if we go back to the example that we have here, notice that the monosaccharides that I gave you here, they're all D monosaccharides, based on the numbering that each of them have. Which carbon is what determines the D configuration for these monosaccharides? Words here. Let's put it in the chat. Which carbon atom determines the D designation on these monosaccharides? Great job, Maria. Great job, Katie. I agree with you. Carbon number 5, that is the chiral carbon that is the farthest away from the carbonyl. And we can see that in all of them, the OH is pointing towards the right. So that's how we determine D and L configuration. Any questions about stereochemistry for monosaccharides? One more thing that I want to mention, and I'm going to write it down here. Most monosaccharides that are found in nature have a D designation. So whenever we find sugars, they're just deep sugars, okay? That's just how nature decided that it's going to work with them, okay? There's no, we could have arguments of like, why is it that is a D sugar versus an L sugar? But for now, understand that this is just something that you should know and memorize, okay? So, the last topic that I want to mention today is the whole idea. Oh, we have 5 minutes. Let's see. No, I think I will mention this. I'm not going to mention the reactions. I'm just going to talk about the reactions next time, and then we move on to chapter 7. So, when it comes to the monosaccharides, the most common monosaccharides that we have are glucose, fructose, and galactose, okay? So what is glucose? And you can see that I put D-glucose because D-glucose is the most common monosaccharide there. We can find it in fruits, we can find it in corn syrup, we can find it in honey. And as we're going to see in chapter 12, that is the preferred sugar that we utilize in order to derive energy. D-glucose is an aldohexose. And as you can see the structure on the right side, it has an aldehyde and it has 6 carbons. And it has the chemical formula C6H12O6. Now, glucose is also known as dextrose. And in the body, when you're getting readings of the sugar in the blood, what they're looking is what are the levels of glucose, okay? Now, glucose is so important because it's the building block of disaccharides like sucrose, maltose, and lactose. And in addition to it, there are many polysaccharides that are made from glucose. So for example, cellulose, which is how certain fibrous structures in plants, it is a structure that comes from glucose. Or glycogen, which is the way that we store sugar, also is a structure that is formed from glucose. Then we have galactose. Galactose has an aldo, it is an aldohexose. It is not found free in nature, okay? How do we obtain galactose? Well, because if you have the disaccharide lactose and then you break it down via hydrolysis, that's how you can obtain galactose. When it comes to glucose and galactose, they're very similar to each other. There's only one difference. At carbon number 4, there is one OH that is pointing in a different direction. So you can see it here. This single switcheroo of OH makes a completely different sugar. So as you can see, the one in glucose is pointing towards the right, the one in galactose is pointing towards the left. And that makes a completely different sugar. That's just an interesting feature and the difference between glucose and the galactose. Lastly, we have fructose, okay? And fructose, as you can see here, is also a hexose, but it is a ketohexose, okay? Fructose, we actually obtain it from a disaccharide that is known as sucrose. And you may be very familiar with sucrose. Sucrose is what we know as table sugar. Now, it's important to note that fructose is found in many fruits. And out of the monosaccharides is actually the sweetest carbohydrate. It is actually twice as sweet as table sugar. That's why if you think about it, since fructose is one of those sugars that is actually naturally found in fruit, that's why fruits are so desirable like to the senses, because fructose is there, and that's why many fruits have that very nice and sweet taste to them because of the presence of fructose in it, okay? Any questions when it comes to the descriptions of the monosaccharides glucose, fructose, and galactose. Great. Since there are no questions, this is all for today.